Okay, the rocket baseball thrower problem. So imagine I have a rocket and it has a number of baseballs in it. And so the rocket itself has a number of baseballs in it. Okay. And it's going to be powered by throwing the baseballs out of the back. Okay? And we have 200 throwers, baseball throwers. The mass of a baseball is 100 grams, and the speed of a baseball is 100 meters per second. And I throw 10 balls per second forever. So, and I'm going to ignore the fact that I can't really carry that many baseballs, but I'm going to just assume that I'm going to do 10 baseballs per second forever. And I'd like to know how far I would go in a week and how long it would take me to go to Alpha Centauri and other things. So what we have here is a conservation of momentum problem. So we start off in this case, and we have everything stationary. So the momentum is 0. Okay, this is the mass times the speed of each thing is 0. I throw something out the back, then there's going to be some sort of recoil speed that's going to happen. Okay, and this recoil speed is going to be a little smaller than the speed that I send this baseball out, because the baseball itself is only 100 grams, and the craft itself is 2,000 kilograms. So if we do conservation momentum, what we have is that the momentum of this system now is negative 100 meters per second times 0.1 kilograms. Okay. And it's negative because we have to take into account direction, and so left is negative. And then we add the recoil speed times the 2,000 kilograms. And this amount of momentum has to be the same as the momentum before, which was 0. So it has to actually add up to 0. And it's easy to solve for the recoil speed, and this is for one baseball. Okay, one baseball, and then I get a recoil speed of 0.005 meters per second. Now what happens when I do 2 baseballs? So now the picture looks a little bit different. Now I have my craft at 2,000 kilograms. I have the first baseball that's flying at 100 meters per second. I have my second baseball that's flying at 100 meters per second. And I have my current recoil speed. So I have the momentum of this one, negative 100 meters per second times 0.1 kilograms. I add the momentum of this one, which is negative 100 meters per second times 0.1 kilograms. I add the momentum of this, which is 2,000 kilograms times the recoil speed, and that all has to add up to 0. And that again lets me solve for the recoil speed at 0.01 meters per second, which, if you notice, is 2 times the 0.005 meters per second. So, you know, what we have is one baseball gives us a certain amount of momentum, which is, and if I'm not changing the mass of the craft, it'll be a certain speed, and then 2 will give me twice the momentum, 3 will be 3 times the momentum, and so forth. And so then we can say that with 10 baseballs, that's going to give me a recoil speed of 0.05 meters per second. And if I have 200 throwers and we have 10 baseballs per second, that's going to give me a recoil speed of 10 meters per second after 1 second. Okay? Now, it's tempting to say, well, I'm going 10 meters per second after 1 second. How far am I going to go in a week? And so in a week, 1 week, converting that to seconds, I just get rid of convert to days, to hours, hours to minutes, times minutes to seconds. 24 and 1, 60 and 1, 60 and 1. And that gets me about 6 times 10 to the 5th seconds. All right. Now, it's tempting to say, well, I'm going 10 meters per second, and so I have this many seconds, that's how far I'm going to go. But the problem with that, and the reason why that would be wrong, so you don't do that, is that, yes, we're going 10 meters per second after 1 second, but we're going 20 meters per second after 2. And we're going 30 meters per second after 3 seconds, and on and on and on. So we keep speeding up and speeding up and speeding up, and so how do we figure out how far we've gone in 10 to the 6 times 10 to the 5th seconds? So the way we do that is we just draw a speed and time plot, and it looks something like this, where after 1 second we're going 10 meters per second, and after 2 seconds we're going 20 meters per second, and so on. So the slope of this line is 10 meters per second change every single second. And so the equation of this line is, and since it has a slope of 0, intercept of 0, we have 10 meters per second every single second, that's the slope, times the time. And the distance at some time is this area. That's the distance, which is 1/2 the base times the height. Now in our case, that's 1/2. The base is the time that we're talking about, which is 6 times 10 to the 5th seconds, times the height, which is the speed that we get after going for a week. And so essentially we take 6 times 10 to the 5th seconds times 10, so we have 6 times 10 to the 6th meters per second. And this will give us somewhere around 2 times 10 to the 12 meters. Okay, so that'll give us our distance. Now, what if I asked, how long will it take me to go somewhere? Well, then what I have is, I have this point here is some unknown time, which means that this is also unknown. I won't have that number, but I can still figure it out. So let's say the distance to Alpha Centauri is about 4 times 10 to the 16 meters, and this is going to be equal to 1/2 the base times the height. The base is time, so I'll just call that t, and the height is the speed here, and so I end up with 10 meters per second every second times t. So I just plugged this as the base because I don't have a number for it. I just plugged that into here, and now I can solve for t. So I get t squared is around 10 to the 16 seconds squared, and so this gives me that time is about 10 to the 8 seconds, or about 3 years. Of course, at some point I'm going to exceed the speed of light, and I'll have problems with this. But up until then, I'll be fine. The key aspect here is that we keep increasing in speed the whole time, and so we need to take into account that fact and essentially the area under the curve. Another way to say that is really I could have taken the average speed, which is 0, and the final speed divided by 2. So I could have taken this final speed divided by 2 and multiplied by the time. And again, it's the same thing as the 1/2 base times the height equation.